Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's activity is a brief tour of the motor family tree. Our objective today is to recognize identifiable traits that distinguish one motor from another and introduce basic concepts and terms to assist you in the task of classifying motors when encountered in their natural habitat. Right up front, I'm issuing a correction about the title of this lecture and the family tree is referring to. It would be more appropriate to call this the rotating electrical machine family tree, where the broader, more universal and holistic title is paying homage to the dual nature of rotating electrical machines, motors on one side and generators on the other. The reason I'm sticking with motor in the title, though, is the same reason beer companies use girls in bikinis to sell beer and not the actual red-eyed and bleary clientele that drink it. It's sexier and more likely to attract interest. Be aware the family tree I'm referring to can easily be extended into the generator realm with very little difficulty. For example, there are three-phase AC synchronous motors and three-phase AC synchronous generators with very little conceptual difference between them besides that of direction. Motors convert electrical power into rotating mechanical power minus losses. Generators convert rotating mechanical power into electrical power minus losses. It's really that simple. There are subtle and not so subtle differences between two machines designed exclusively for one task and not the other. But for the most part, a high-level discussion like this can encompass both aspects. Staying with the motor designation, however, we can say we're talking about a type of actuator, where the term actuator is a blanket level term meaning a device that can take one form of input and transform it into mechanical output. We could parse the whole actuator designation up using several different perspectives. For example, what is the type of input energy? Electrical, hydraulic, pneumatic, thermal, chemical, etc. Also, we could divide these actuators into the type of mechanical output they produce. For example, linear, rotational, or oscillation, which is a form of partial rotation. A hydraulic cylinder is a classic example of a linear actuator that translates hydraulic input into linear mechanical output. The hydraulic cylinders lecture, available at the Big Bad Tech channel, deals extensively with this type of actuator. A motor is an electrical actuator that produces rotational mechanical movement. Keep in mind, additional mechanical linkages can modify the initiating motion. For example, a rotating electrical motor could drive a conveyor belt in a straight line with a belt and pulley combination, or a linearly actuating hydraulic cylinder could tilt a load using pivoting trunnion or clevis mounts. This mechanism is used in a modern horizontal axis wind turbine to pitch the blades into or out of the wind. The branch of the actuator family we'll be talking about today, however, uses electrical input to produce rotational mechanical output. This is my definition of a motor. Regardless of the later branches within the motor family tree, every one of the devices we'll be discussing today does exactly that. The only distinction being the method of doing so based upon construction. The motor branch of the actuator family tree is like the beetle family of insects, which even if you combined every other species on Earth, beetles would still outnumber them like 8 bazillion to 1. Motors are everywhere and do everything to keep our society running. It's absolutely imperative you as an aspiring or practicing technician understand how motors do what they do and recognize what is wrong if they don't. Most reputable electrical engineering technology programs include DC motors in their first quarter basic electronics class and AC motors in later AC electronics classes, or at least say they do in their syllabus. I'm willing to wager that very few of them actually get there. The class often bogs down in tangentially related topics like mesh and nodal analysis and resonance and filters. I am not saying that these topics are not applicable to technicians in certain career fields, but I am saying that motors are more important to most technicians regularly tasked with the maintenance, upgrade, repair, installation, and troubleshooting of motors and motor control systems. Without at least introductory exposures to motors, it's like you're graduating bear hunting school having never once seen a bear in your life. That's exactly what I want to do today. Look at the bear family in great detail so we can figure out their feeding habits, favorite watering holes, and what exactly they do in the woods. Later in life, when you're traipsing around a snow-covered plain and encounter a large white bear feeding upon the carcass of a seal, I want you to have the confidence to say, "That's a polar bear." And when someone in your party of dubious bear knowledge has the audacity to say, "No, I think that's a gummy bear," you can present them with the facts in a courteous and professional manner and aid them in their understanding that this large white bear feeding upon a seal in the snow is a polar bear and not a bear-shaped gelatinous goo largely composed of high fructose corn syrup, boiled horse hooves, and dye. The first question any aspiring bear hunter may ask is, what do bears look like? The same can be asked of motors. Externally, a motor has a body, a shaft, and electrical connections. The body could be little, big, red, blue, roughly cylindrical, or maybe even pancake-shaped, but normally it's the large part that doesn't move and is normally attached to something big like a frame or a floor. It could be attached with feet, a frame, or a faceplate. The shaft is the spinning thing that sticks out of the body, and the shaft is normally attached to something that needs to be spun. Most of the time there's a key or keyway on the shaft to directly couple the shaft to the load, a coupling, or perhaps a gear or gear set to increase torque and decrease speed, or the other way around. A coupling compensates for misalignment of the shaft with a load and enables a technician to take it apart. The gearbox and coupling aren't actually part of the motor, but they're essential for the motor to do its job. The job of the motor is to convert electrical input into rotational mechanical output. This mechanical output, as we'll learn in later lectures, is characterized by two measurable quantities: a twisting force known as torque, measured in units of Newton meters or foot-pounds force, and rotational speed, typically measured in units of revolutions per minute. Externally, just like all bears are furry quadrupeds, most motors kind of look the same. Despite the fact that there's a bazillion different sizes, color schemes, and manufacturers, they all kind of boil down to something with a shaft that sticks out of it and spins. I know you can shave a bear and teach it to walk on two legs, so there are going to be obvious exceptions to our general description, but for the most part, motors look like this, and all motors produce mechanical power output in terms of torque and rotational speed. We've got to skin these things to really identify the differences. Obviously, skinning a live bear may be a hazardous in practicality, and taking apart a functional motor is kind of a pain. So the next best question an aspiring bear hunter may ask is, what do bears eat? The same can be asked of motors. This will give us clues to their internal construction without having to take them apart. Obviously, a motor uses incoming electrical power as its input, so it stands to conjecture there may be motors that prefer AC and those that prefer DC. This is the most prominent distinction. Additionally, we can divide AC into two branches: industrial three-phase AC motors and domestic single-phase AC motors. We've now divided our motor family tree into three distinct branches, and there is very little crosstalk between them, with one major exception being the universal motor, which, as the name implies, can run off DC or single-phase AC. If being an electrical engineering technician was easy, everyone would be an electrical engineering technician. So we've got to throw a couple impediments in the way of those studying this topic and make the terminology as confusing as possible. The first hurdle is what the different branches of the DC-AC split call the rotating parts and the stationary parts of the motor. On the AC side, it's pretty easy. The rotor is the rotating part, and the stator is the stationary part. On the DC side of the split, the armature is the rotating part, and the field windings are the stationary electrical part. If you use the term armature to describe a rotor on an AC machine, people will probably understand what you intend, but it's generally not considered good form to do so. The next question an aspiring bear hunter may ask is this: where them bears at? My answer is, I don't know. What type of bear do you want to hunt? Do you want to hang a polar bear head over your imposing fireplace, or do you want a koala bear? Do you work at a manufacturing facility that uses three-phase AC? Chances are you need to learn about the three-phase AC squirrel cage induction motor. Do you maintain a large-scale hydroelectric generator? chances are you need to learn about three-phase AC, synchronous motors, and generators. Do you work on wind turbines? Chances are you need to check out the three-phase AC permanent magnet synchronous motors and generators, or three-phase AC wound rotor induction motors and generators central to doubly fed induction generation. Are you an electric car enthusiast? Chances are you need to learn about brushless DC motors, which in actuality are DC motors with integral power electronics very similar to three-phase AC permanent magnet synchronous motors. Do you want to fix your vacuum cleaner? Chances are you need to check out single-phase AC motors. If you have no idea where you want to go, my recommendation is to head straight for Nikola Tesla's invention, the three-phase AC squirrel cage induction motor. Of the beetle family, this is the LBB, little black beetle species, which even if you combined all other species on Earth, the LBB would still outnumber them 7.9 bazillion to 1. It's not exactly the easiest motor to understand, but it is the most popular motor in the known universe. If you can understand how it works, chances are the rest of the motor family tree will be low-hanging fruit. It is for this reason I typically start an in-depth discussion of motors with the three-phase AC squirrel cage induction motor. This implies a train load of baggage precedes this first lecture, and that I would prefer any student making use of it have a requisite knowledge of DC, single-phase AC, and three-phase AC circuit analysis. This isn't always the case, and if you just blew in from some random corner of the internet and your interest is exclusively one-sided, please stick with me for a moment, because this lecture is meant to be a familiarization only and does not go into a lot of technical detail. The three-phase AC side of the motor family tree is characterized by a rotating magnetic field. Later lectures will discuss this phenomenon in greater detail. The term synchronous speed is the rotational speed of the magnetic field. It's a handy reference point for the speed of the motor, which we'll see in a little bit may or may not be synchronized with the synchronous speed, or may slip behind it, or ahead in the case of asynchronous generation. The synchronous speed can be determined by the input AC frequency and the number of poles per phase, or as I prefer, the AC input period and the number of pole pairs per phase, since the north must accompany a south and vice versa. The stator, or stationary windings, create this rotating magnetic field. What's so especially awesome about this field is that it's smooth, strong, and capable of being reversed simply by interchanging any two stator leads inside a three-phase AC system. The division I'm drawing between the synchronous side and the induction side of three-phase AC motors is based upon performance. Synchronous motors' rotational speed is synchronized with that of the magnetic field. Induction motors are not, and by necessity, they must lag behind or leap ahead in the case of generation for them to function at all. A synchronous motor essentially has magnets on the rotor. There are electrically excited versions that use an external DC source to create an electromagnet, and there are non-excited versions which use a permanent magnet or magnets on the rotor. This division is not meant to be exhaustive. Be aware there are self-excited rotors, reluctance and hysteresis motors, but I really only want to concentrate on the DC-excited rotor and the non-excited permanent magnet rotor for now. The permanent magnet rotor is easy to visualize. It's a magnet with a stick on it. The excited electromagnet is also easy to visualize once we discuss the rules governing electromagnetic interaction in later lectures. Getting the electricity to a rotating rotor, however, presents us with our first structural modification. How do you send DC electricity using two wires to something that revolves 360 degrees without twisting the wires into a knot? The device that allows one to do so is known as a slip ring. A slip ring is a means of electrical connection between a rotating and stationary member. There are several different forms of slip rings, but the most basic configuration is a conductive ring on the rotor shaft which connects to the necessary parts of the rotor. Riding on this conductive ring is a conductive brush being pushed into place by a spring and brush holder combination electrically connected to the stationary electrical inputs. This way, regardless of orientation, the stationary electrical signal is routed to the correct rotating part. This structure is not confined exclusively to the electrical world either. Hydraulic energy is transferred between rotating members and stationary members using a hydraulic rotational coupling. In contrast to their electrical relatives, these are leaky, nasty, messy things that you cannot come away from not covered in oil. Most rotating hydraulic unions include numerous dynamic seals and a case drain to account for this leakage, but that just gets the big stuff. Electrical slip rings ideally don't leak electron juice everywhere, but they're not maintenance-free by any means. The brush itself is a consumable. At a certain point in its lifespan of rubbing its head on a ring while a spring is pushing on its feet, it's going to get shorter and shorter and eventually cease to function. All those brush parts being rubbed off have to go somewhere, and they accumulate as an electrically conductive dust wherever it's the worst place to congregate. A large portion of low-level maintenance performed on motors and generators is simply replacing the brushes and cleaning out brush dust. Inside its operational range, a synchronous motor can be expected to match synchronous speed of the rotating magnetic field regardless of the applied load. Obviously, the electrical input requirements will change because increased power output requires additional input from somewhere. These devices are not magic though, and have practical limits only under which they can perform as advertised. Pullout torque is the point at which a synchronous motor is so loaded that it pulls out of synchronization. You'll immediately be aware of this event because of the change in electrical characteristics, horrendous noise, and your lab instructor's boot planted firmly in your butt telling you to shut her down. Experimental verification labs may ask you to determine the pullout torque for a synchronous motor, but realize this isn't something you want to do every day. Given a rotating magnetic field is produced the instant full voltage is applied to the stator windings, already revolving at synchronous speed, it would be understandable that a rotor, an applied load with static inertia, may take some time to come up to this speed. It's like having your buddy take you water skiing, but only tossing you a rope as he passes the dock at 60 miles per hour. It's going to rip your balls right out of your sockets if you try to accelerate this fast, and there might be better ways to reach this acceleration. Perhaps the rotating magnetic field of a synchronous motor could be slowly accelerated using a variable frequency drive, or maybe the rotor could accelerate itself to something very close to synchronous speed via other means before the electromagnets on the rotor are excited. We'll deal with these characteristics in later lectures, but realize that the desirable stable speed characteristics of a synchronous motor come at a price of slightly more complicated means of starting. On the generator side of the equation, the synchronous generator is what produces most of the electricity in the world today. If additional generators come online, they must first be synchronized to grid-appropriate voltage, frequency, phase sequence, and phase shift using a synchroscope. Permanent magnet synchronous generation with full conversion is performed on some wind turbines where varying speed wind produces three-phase wild AC, i.e. electrical energy without regard for voltage, frequency, phase shift, or phase sequence. This three-phase wild AC is completely converted into DC and then again completely converted into grid-compliant three-phase AC with the appropriate voltage, frequency, phase sequence, and phase shift for export. In addition to their role as motors and generators, synchronous machines also fulfill another role that none of the other devices we're talking about today can do. This role is that of a synchronous condenser. A synchronous condenser is a very neat device that performs power factor correction for another electrical load by varying whether it supplies or consumes reactive power, i.e. acts as a capacitor or an inductor. Ideally, the resultant power factor is corrected back to unity. A synchronous condenser is essentially an unloaded synchronous motor whose excitation current, i.e. the current that directly influences the resultant strength of the rotor magnetic field, is varied as seen fit to correct the combination towards unity. This is really neat. We'll go into this special application in later lectures. The induction side of the three-phase AC motor branch uses different means of producing an electromagnet on the rotor. Obviously, the means of doing so is via induction. Induction is a fancy term used to describe a magnetic, not physical link between two circuits. This is really neat stuff. For those that have an understanding of a transformer, this is exactly what's happening between the stator and the rotor in a three-phase AC induction motor, just like the magnetic link between a primary and secondary coil in a transformer. Time-variant AC current inside our stator, the primary winding, produces a time-variant magnetic field. Given the rotor, our secondary winding is inside this magnetic field, there will be a resultant voltage polarity and current induced via Faraday's law of electromagnetic induction. Because current is now flowing in our rotor, it will now generate its own magnetic field. This magnetic field on the rotor can be attracted or repulsed to the rotating magnetic field that initiated the whole thing in the first place. This is mind-blowing stuff, and it took a genius like Nikola Tesla to figure it out in the first place. Long story short, you don't need any physical connection to the rotor at all for a three-phase AC squirrel cage induction motor. This greatly simplifies maintenance and starting, however, comes at a price. The rotor rotational speed is not nearly as stable as a synchronous motor and varies positively or negatively as the load is removed and applied. What's totally crazy is that the rotor, even unloaded, must necessarily lag behind the synchronous speed of the rotating magnetic field and consume reactive power for the induction process to work at all. We'll go over the details behind this in later lectures. The wound rotor induction motor is for the most part exactly like its brother, the squirrel cage induction motor, with two notable exceptions. One, the rotor isn't a heavy squirrel cage looking thing that is difficult to manufacture for large motors. It's typically a lightweight construction that is composed of wire wound around a laminated iron rotor that is vastly easier to manufacture. Two, there exist connections to the rotor. These connections can short-circuit the rotor so it behaves exactly like a squirrel cage induction motor, or add resistance to the rotor to vary the starting characteristics and operational speed of a wound rotor motor, or, in the case of doubly fed induction generation, act as electrical inputs to the rotor as well as stator, hence the term doubly fed. Long story short, if your three-phase AC motor has two connections to the rotor, chances are it is a synchronous motor, and those slip rings are the positive and negative connections for the DC energy used to electrically excite the rotor electromagnets. The windings on the rotor might also be visible. Speed should be constant for a given operational range. If your three-phase AC motor has no electrical connections to the rotor, and you can see permanent magnets on the rotor, chances are it is a permanent magnet synchronous motor. Speed should be constant for a given operational range. If your three-phase AC motor does not have connections to the rotor, chances are it is a squirrel cage induction motor, where the rotor must necessarily revolve slower than synchronous speed for the induced electromagnets in the rotor to work. Loading this motor up slows it down. Unloading this motor speeds it up. If your three-phase AC motor does have connections to the rotor, notably 3 or more for three-phase AC, chances are it is a wound rotor induction motor. The rotor still must also necessarily revolve slower than synchronous speed. However, one now has access to the rotor to vary the starting characteristics and operational speed. On the other side of the motor family tree are several different configurations of DC motors. Since a DC supply voltage is of constant polarity, these devices are not powered by a rotating magnetic field, the brushless DC motor being somewhat of an exception, which we'll talk about in a moment. They are, however, powered by a magnetic interaction between the armature and field windings. If we remember correctly, the armature is the rotating winding of a DC motor, and the field winding is the stationary winding of a DC motor. All the armature and field windings do is create electromagnets that can interact based off their degree of misalignment or alignment with each other. The differences within the DC side of the family tree primarily result from the electrical arrangement of the armature with that of the field winding. Keep in mind these relationships between armature and field windings are only electrical in nature, and they interact with each other in physical space. The armature physically rotates with respect to the field winding regardless of its electrical configuration. We'll come back to a device that allows this to happen, called the commutator, shortly. The armature winding could be in series with the field winding for a series DC motor. The current through the armature and field will be the same. The armature winding could be in parallel with the field winding for a shunt wound DC motor. The voltage across the armature and the field winding will be the same. Additionally, there could be both a series and shunt winding in a compound DC motor, and that shunt winding can encompass both the series and armature winding in a long shunt compound DC motor, or just the armature winding in a short shunt compound DC motor. The shunt and series windings inside a compound DC motor can either aid each other in the case of cumulative or oppose each other in a differential configuration. Other configurations include a very easy to understand arrangement called a separately excited configuration, where the armature is fed from one source and the field is fed from another entirely separate source. One could also replace the field winding with a permanent magnet for a permanent magnet DC motor, or even replace the armature winding with a permanent magnet and power the field with DC that is then inverted with integrated power electronics, so it almost acts like a permanent magnet synchronous motor. The brushless DC motor is still lumped into the DC family because the power electronics performing the inversion are integrated, meaning a permanent functional part of the device. All these different configurations produce different speed and torque profiles and inherent advantages and disadvantages, which we'll discuss in later lectures. Key to the functionality of every single DC motor, with the obvious exception of the brushless DC motor, obvious because there's no brushes, is the commutator. Since the DC motor is powered by DC, the polarity of the applied voltage never changes. And the field winding, being a fixed winding, never changes physical position. Therefore, the resultant magnetic field produced by a winding subjected to this constant polarity voltage never changes. The field winding, being the fixed or stationary winding, never changes the location or direction of the magnetic field. Keeping it very basic, if we were to create a stationary field winding consisting of two fixed magnets in close proximity to a third rotating magnet, the magnetic fields would interact such that the norths are attracted to souths and vice versa. Once the armature achieved this alignment, the magnet would just sit there and do nothing. Not exactly the best motor if all you can get out of it at maximum is a single 90-degree turn. The commutator is a pretty cool little device that mechanically switches the direction of current to the armature just before it aligns. If current switches direction, magnetic polarity switches, and we're right back to where we started, wanting to turn towards alignment. Just before it gets there, though, the commutator switches direction again, and you guessed it, we're right back to where we started. This process happens over and over, and obviously does so at a great rate of speed, so the resultant torque and rotational speed is not pulsed and jerky. The commutator does this by selectively connecting or disconnecting certain windings inside the armature, so they're producing magnetic misalignment with the field, then the shaft turns towards alignment. When the shaft turns, the brushes move along the commutator to another section of the armature winding that produces a magnetic polarity that is misaligned, and the process repeats itself. The commutator is sectioned off between conductive and non-conductive portions and looks totally different than the slip ring we saw on the synchronous and wound rotor induction motors. Those slip rings were a smooth, single connection regardless of rotational position. The commutator is very plainly divided. The commutator purposely makes DC change which winding it's going through depending on rotational position. It's very similar to a slip ring in that it allows electrical connection from a non-moving DC supply to a rotating armature, but totally different and immediately recognizable because of the different sections on the ring. Finally, everyone has relatives they are not proud of. You know, the crazy cat aunt, the uncle that can't be within 1,000 feet of a school or a park frequented by children, and all those malfunctioning, substance-abusing, new age cult, gluten-free, animal-free, hygiene-free hippy-dippies, or perpetually pissed-off, paranoid gun-nut cousins you'd rather not have at the Turkey Day table. Single-phase AC motors? That's them. They are the malformed mutant cretins locked in the basement of the motor family tree that I do not want to talk about. These, like their industrial three-phase AC cousins, also use a rotating magnetic field, but to do so with a single phase requires contrived methods bordering on the hokey and undignified. Sure, you can teach a chimp to ride a bike, but I'd be less than confident of a chimp's ability to fly a passenger jet. The rotating magnetic field produced by a single-phase AC stator is jerky, not smooth, and I plain just don't like them. That being said, if a single-phase AC motor is all you've got, they get the job done and produce rotating mechanical output just like the rest of the motor family tree. There are numerous ways of creating single-phase AC motors, like cap starts, cap runs, and all sorts of other incantations. But I am encouraging you not to even worry about these bike-riding chimps till you've got absolutely nothing better to do than go to the circus and watch them fling poop at each other. The increasing availability of a power electronics device known as a motor drive or variable frequency drive is making the functionality of three-phase AC motors available for applications using single-phase AC. A motor drive is essentially a rectifier that converts incoming fixed single-phase AC or three-phase AC into pure DC, then inverts this DC energy into variable three-phase AC within an adjustable magnitude and frequency. Increase the frequency, the motor speeds up. Decrease the frequency, the motor slows down. The motor drive isn't really part of the motor, however, it's essential to governing its torque and rotational speed performance. The inversion half of the power electronics inside a motor drive are essentially what does the conversion of DC input to multi-phase AC for a brushless DC motor. Straddling this no man's land between the single-phase AC motors and DC motors is the universal motor. As the name implies, it can be run on DC or single-phase AC. Just like cutting a fish in half and sewing it to half a monkey, it doesn't swim well, nor does it ride a bike well, but it does both swim and ride a bike. The universal motor is really just a series DC motor, think commutator, with compensating windings on the field windings designed to minimize inductive losses when run on AC. We'll go into this device in greater detail later. That about wraps it up for our brief tour of the motor family tree. Yes, there are gaping holes and missing branches, but for the most part, these are the ones you will most often run across. In conclusion, this lecture accomplished a brief tour of the motor family tree. Along the way, we learned to recognize identifiable traits that distinguish one motor from another. Additionally, we introduced basic concepts and terms to assist you in the task of classifying motors when encountered in their natural habitat. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.